Hi guys. So today's lecture will be introducing you to two new data structures, a stack and a queue. So if we go to the slides, a stack and a queue are both data structures, just like the array list and the linked list that we previously covered. And just like an array list and a linked list, they hold a collection of data or elements. And they have operations on that data. And these operations and methods are once again defined by Java's collection interface that we went over in the linked list lecture. But what you'll find is there's actually some operations or methods that are specific to the stack and the queue data structures. And we'll look at what those are in a second here. Stacks and queues are often taught together due to their similarity. And they're both data structures that enforce the order in which data is allowed to leave the data structure. This will make more sense when we start talking more and more about what a stack is and what a queue is. But just remember that the relation is how data is allowed to leave the data structure. So we'll talk about, I wanted to start off with analogies for both the stack and the queue. Starting with the stack analogy, stacking concrete blocks. You can't pull blocks from the middle or the bottom of this stack, right? So if you imagine you have concrete blocks and you stack one on top of the other, if you tried to pull out the bottom block, concrete blocks are just too heavy. You can't do it. And even, a block in the middle, it'd be very hard to just yank out a concrete block. So instead, what you have to do is, if you wanted to, say, reach some block that's in the middle of this stack, you would have to remove the topmost block, then remove the next topmost block, and so on and so forth until eventually you reach the desired block that you want to remove. So if you want to remove a block, you must pull off the block at the top one at a time until you have reached the desired block to remove. In other words, the block at the top was the last one in and is therefore going to be the first one out. There are many stack analogies. There's a very common one that uses plates instead. I'm sure if you do some searching on your own, you'll come across that analogy. The queue analogy is pretty simple. It's just a line, right? So it's waiting in a line. The person at the front of the line is the first one who's been in the line. Is the person who has been in the line the longest, in other words, was the first one to enter the line, or the first in. And accordingly is going to be the first one to leave the line, first out. And so this first in and this first out, you'll see in a second here why I specifically say first in, first out. It relates to an analogy that's used to describe a queue, and we'll also go over an analogy that describes a stack. But so you can think of a queue as basically just as a line. Somebody gets in line, they wait for their turn, and eventually, when they're at the front of the line, they get to leave the queue. So I did say stacks and queues are taught together due to their similarity, but it's not just that they're similar, they're in fact, their relationship is that they're opposites. And so in order to understand how they're opposites, you have to understand these two acronyms. LIFO, sometimes called LIFO or LIFO, however you want to say it, versus FIFO, you can also call that FIFO or FIFO. So we'll start with the first acronym, last in, first out, LIFO. The last element in the data structure must be the first one to be removed. You can also call this acronym FILO, first in, last out. They mean the same thing. The idea is whatever data was most recently put into the data structure will be the first one to get removed when the user of this data structure desires another element out of it. Now, first in, first out, the next acronym, FIFO, is in a way the opposite. So the first element in the data structure must be the first one to be removed. So this, again, is pertaining to the queue, whereas the last in, first out is pertaining to the stack data structure. And so yeah, the first in, first out, like I had previously said, a data element goes into the data structure, and for it basically will have to wait its turn until eventually it reaches the front of the data structure and gets to be removed from the first in, first out data structure. And the one that we're covering specifically is the queue. There are other data structures that follow these formats, but we're only going to worry about the stack and the queue. So, specifically talking about a stack is a data structure in which items are only inserted on or removed from the top of a stack. And so you can imagine, if we go back to this concrete block analogy, replace those concrete blocks with actual data in your mind, of course, right? And what you'll see is, data stacked on top of each other, and only the data at the top of that stack gets to be removed. Or if you're going to insert an item or an element, it only gets to be inserted to the top of the stack. And so these are the three methods that I had previously talked about that are specific to a stack. And the first one is push. And so basically this operation inserts an item onto the top of the stack. There is a pop operation, and this removes and returns the item at the top of the stack. And then there's a peek operation, and this returns the item at the top of the stack, but does not actually remove it. It lets you peek at the top element. And so a stack can actually be implemented using another data structure, one that we've already covered, called a linked list. Or you can use an array or an array list. And so yeah, this brings up a good point. You can use other data structures to help implement another data structure. Well, why would you want to do that? It's not really going to make sense to you right now because we haven't gone over algorithmic complexity, which we will in a few lectures. But once we do, you'll understand why all these different data structures exist. And why using one data structure to help develop another data structure is viable. So here's an example of the stack. Starting from left and then going to the right, you have a push operation. We're going to say our elements are just integers, and we're pushing the element 4. And so you can see the top of the stack, while I have it, all the way at the top here, really the 4 that we just pushed onto the stack is both the top and the bottom. Moving on, we push a 7, and so now the 7 is at the top of the stack, and 4 is at the bottom of the stack. Once again, we push 2. Push 2 gets pushed onto the top of the stack. So you can say basically 2 gets pushed onto the 7, right? But now 2 becomes the top of the stack. And then we push 13 and the same thing occurs, but the 13 gets pushed onto the top of the stack. And then looking at the pop function, or method, or operation, whatever you want to call it. So here's the starting stack. You'll notice it's the same one we ended off with before. If we run the pop operation, notice the pop operation does not take an input. And the reason why it doesn't take an input is because it only ever will remove the top of the stack. And so we run pop. and what it will return is 13, because 13 is what was at the top of this stack. We run pop again. So remember, this pop operation is referring to the remaining elements in this stack here. And so it will return 2, resulting in these elements remaining in the stack, the 4 and the 7. And then we run pop again, and then it will return the 7. And what remains is just the 4. And then, of course, if we ran pop again, it would return the 4. And then there would be nothing in the stack. And so this is conceptually how you can think of a stack working with data and elements. So moving on to the queue data structure. A queue is a data structure in which items are inserted at the end of the queue and removed from the front of the queue. So we're going to use the same terms, push, pop, and peek, for these operations, but the queue sometimes calls these methods something different. There doesn't seem to be quite as solid of a standard for queue operations as there is for a stack. So we'll call them push, pop, and peek here, but then in my example I'll actually refer to them in other names, such as enqueue and dequeue. So the push operation inserts an item at the end of the queue, and this is the one that sometimes is referred to as enqueue. It's enqueuing, it's putting something into the queue. The pop operation removes and returns the item at the front of the queue. And so notice the big difference between the pop operation for the queue as opposed to the pop operation for the stack. The stack's pop operation removes and returns the item at the end of the stack, or the top of the stack, whereas the pop operation is removing and returning the item at the front of the queue. So basically other ends of where the data is stored. And this pop operation is sometimes referred to as a dequeue, removing something from the queue. And then the peek operation does the same. It returns but does not remove the item at the front of the queue. It allows you to peek at the next element to be removed. And a queue can also be implemented using other data structures, such as an array list, or an array, or a linked list. So looking at the queue example, if we enqueue 4, the result is our queue has only a single element, so this single element is both at the end and at the front of the queue. But now if we enqueue a 7, the 7 goes in to the end of the queue, and our 4, who's been in the queue the longest, remains at the front of the queue. Now if we enqueue a 2 is now at the end of the queue because it was just recently added. And accordingly, the queue, or if you want to go back to the analogy that I made, the line, right? 4 has been in the line the longest. So accordingly, it's at the front of the line. Therefore, the next element to get removed from the queue when it should happen should be the 4. And then last, we enqueue a 13, which once again goes in at the end of the queue. And now if we look at a dequeue example, so at the top here, this is our starting queue with elements inside of it. You'll notice it's the same order and same elements from the last example. And if we run dequeue, once again notice no input here. That's because it's removing and returning the element at the front of the queue. It will return 4 because 4 is at the front of the queue. Now if we run dequeue again, it would return the 7 because the 7 is now at the front of the queue. And if we run dequeue again, it will return a 2 because 2 is now at the front of the queue. If we dequeued one more time, then the 13, since it is at the front of the queue, it's the only element in the queue, that would then get returned by dequeue. So we can go ahead and look at Java's documentation for stacks and queues. And you'll notice some differences in the method names and how they might be handled. Go ahead and exit out of this. We go to the stack. This is Java's documentation. You'll notice, right, we inherit from the collection and the abstract list. We inherit from something called a vector, which we don't really need to concern ourselves too much with right now. And then here we are, the stack. So if we read about the stack class represents a last in, first out stack of objects. It extends a class vector with 5 operations that allow a vector to be treated as a stack. The usual push and pop operations are provided, as well as a method to peek at the top item on the stack, a method to test for whether the stack is empty, and a method to search the stack for an item and discover how far it is from the top of the stack. This is something that seems to be relatively inconsistent within Java right now. They provide a slightly different data structure that is apparently a more complete and consistent set of LIFO stack operations, which is in the DQ interface, and they provide an array DQ data structure, and we don't really need to concern ourselves with this right now. But if we go ahead and look at the methods we have, there's an empty method that's checking to see if the stack is empty. There's the peek, the pop, and the push, and also a search method. And these are the primary methods for the stack, and we've already covered these 3, right? Now what's interesting is just a design decision that they made. If you look at the push, it's returning an element of type E, which is the item argument. So what the item argument that you put in is what gets returned, which is rather odd in my opinion. But I'm sure they have good reason for this design decision. And you can read a description of the push method, right? It says pushes an item onto the top of the stack, exactly what we previously talked about. I mean, this has exactly the same effect as add element, which is just another method designed by another interface. And if we look here, these are all the methods given to us by this vector class. And you'll notice a lot of these methods you should have already seen before with the array list and the linked list. And so these are all methods provided to us by the collections interface. Add all, etc. Now, if we look at the queue, interestingly enough, Java specifies its queue to be an interface. And then after that, you have classes that are specific versions of a queue. If we go ahead and look at the methods, you'll notice the methods are somewhat different. They've got Java still has the peek method, but they have a pull method and a remove method, which are doing almost the same thing, and they're essentially the same thing as what we had called a DQ, or the pop. So and then they also have an add method, which essentially is like the enqueue method. So a lot of different naming differences here, but they all basically do the same thing. Once again, this interface, you get some methods from the collection interface. And if we look here, all known implementing classes, so these are the classes that implement the queue interface, and there's lots of different versions of queues. A big one that you'll probably learn more and more about is the priority queue. This queue is used a lot. I mean, as I'm sure you can imagine, a priority queue that affects your daily life is the waitlist system at San Diego State. That's a priority queue, right? You can enter the wait list pretty early on, but someone else may be ahead of you simply by whatever metrics they use in their priority system or the priority queue. But we're not going to go over a priority queue, just because that's something you learn more about in the data structures course. So I'm not going to program a stack or a queue for you. That's something you'll learn more and more about in data structures. But if you wanted to go ahead and give it a shot yourself, here are some tips. When creating operations for data structures, we should always be asking ourselves a series of questions. What different states can the data structure exist in? And by that I mean, if the data structure is currently empty, has nothing in it, what behavior will this operation have? If the data structure, has a set size, right? And that data structure is now full, or a set capacity, and that data structure is now full, what should the behavior of this operation be? If this data structure should dynamically grow, right? What should the behavior of this particular operation be? There's a bunch of different, I call them states, but they're basically instances of existence, right? For a particular data structure, and any operation in a data structure should care about the current state of that data structure. And so how will this affect the operation that I'm currently working on, and how might someone use this operation to break my data structure? And that this is talking more about edge cases. What would happen if somebody tries to, let's say our data structure uses indices, right? Or I uses the concept of indices, kind of like an array list, right? But then they provide an index that's completely inappropriate, for example, like a negative index or something along those lines, right? How are we going to handle that? And so every time you write a method for a data structure, you should always be concerning yourself with these edge cases and okay, what if the data structure is under this state, how might this operation be affected? Keep this in mind when you go into the data structures course, or if you feel like implementing your own stack or your own queue. You'll find the stack and the queue aren't terribly difficult to implement, but they definitely will take a little bit of time for you guys. That concludes this lecture.